Hi everyone, thank you for coming to this talk. So yeah, I guess you already read the title, so I won't repeat it. A couple words about myself. So I work in Programming Languages and Tools lab at JetBrains Research. Sorry, it happens from time to time. I do research, and my research interests are aligned around the programming languages, weak memory concurrency, compilation correctness, functional programming, and I identify myself as a proof engineer, not software engineer, in the sense that most programs which I write are proofs, mostly I'm writing language. In the language called Coq, which is proof assistant, which allows you to write programs which are also proofs for some statements in constructive mathematics. But this is not the topic of today's talk. Today we're going to speak about weak memory models, more specifically about programming language memory models. So let's dive in. By the way, if you have any questions, please interrupt me and I'll answer to them. Okay. So as all of you probably know, performance of CPUs does not improve as fast as it used to, single core performance. However, nowadays we may get CPUs with like dozens of CPU cores, unlike like 30 years ago. So that's why concurrent and parallel programming is like very hot topic for like at least 15 or even more years. So why is that? Because apparently it's one of the main approaches to increase performance of your code. Yeah, so if you want to write very, very performant code, you from time to time need to get to shared memory concurrency. Shared memory concurrency is actually quite complicated, so it's very easy to write a program which does not what you want. It may have like very subtle problems. So it's extremely important to be able to reason about such programs precisely. So that's why we need to have very formal, very precise models of shared memory concurrency. The name which we'll use to define semantics of concurrent systems like CPUs or programming languages with concurrency, it will be memory model. So the first memory model was introduced by Leslie Lamport in his 1979 paper called How to Make a Multiprocessor Computer That Correctly Executes Multiprocess Programs. So from the title, it looks like the problem was already solved there. And Leslie Lamport came up with the only solution. However, as we will see, it's not the case. So what was proposed in the paper? So there was proposed a memory model called Sequential Consistency, and this is how people usually think about concurrency. It's very intuitive, and it assumes that every execution of concurrent program could be explained as some interleaving execution of its threads. And the idea to model it, we could use this diagram. So here you have like a bunch of CPUs and some global memory, and each access from CPU to memory is either atomic read or atomic write. Atomic in the sense that it happens right away once CPU issued the corresponding request to memory. So now let's consider some programs. So here we have two memory locations, data and R. We may think that R is not actually like a location memory, but a local register. And the idea is that we want to transfer some data from the left thread to the right one. So if you know about concurrency programming, you may say that this is a bad program because there is a race condition on this location data. And what it means that we may get some strange results. And usually, software developers are discouraged from writing such programs. So, for example, if the data we are trying to write to the location data is bigger than machine word, then it may happen that this write will be split to 2 writes in the memory, and this will allow to read in the right thread something which is not this value or the initial value which was written to the location data. To solve this data race, people use locks, and usually we have some lock method and unlock method, and if the methods are properly implemented, then they'll guarantee that there is some order in which these left and right threads accesses to data will be performed. So there will be no concurrent access to the data. And now let's consider some of the most basic locks. Peterson lock, and its simplified implementation could look like that. So we have a flag memory locations. For each CPU we have its own flag, and they also have a shared turn memory location. And the idea is that once the threads started, they set their own flag to 1, saying that they want to acquire the lock. Then they say that now it's actually the turn of the other thread to execute the critical section, the part of the code which is guarded by lock and unlock instructions. So after the CPU on the left performs these 2 instructions, it busy waits until the flag of right thread is assigned, and it's the turn of the right thread. In the end, we set the flags to 0, stating that we no longer need we no longer need to access the shared location. Yeah, I guess it should be clear that in general it should work, and in sequential consistency it works. However, if we'll write this program in C and execute, for example, on my machine, then we'll get something strange. So let's take a look what's happening in the program. So here we have the main procedure, and what it does, it first initializes some locations, then spawns thread 1 and thread 2 functions, and then waits until they are finished, and then we increase the counter. So let's take a closer look what is going on there. So actually we have 2 arrays, A and B, which will replace our data location which was used on the slide. These arrays are initialized by 0 before we execute each instance of the test we wrote. And in the thread functions, what we do exactly the Peterson lock and then unlock. And in between, in the thread 1, we are writing something to the thread B, namely 1 and 1. And then in the right thread, we read from this array B and write it to array 1. So if the Peterson lock is implemented correctly, then the only outcomes which we are allowed to have are either to get A being equal to 0 in both locations in the array, or it being equal to 1 in both locations. But if we see anything else, then we stop our loop and print the number of iterations on which something strange happened. So if we execute this program, first compile with G++ and then execute, then we'll see that after 18,000 iterations, there will be some iteration, then we'll get some other result. So it means that there is something wrong with the implementation of the lock. So let's understand what's going on there. To understand what's going on here, let's take a look at like a smaller fragment of the lock implementation. So here we have just accesses to flag 0 and flag 1, actually the first two accesses in the corresponding threads. So let's just deduce them to a separate smaller program and see what's going there. So suppose we have two locations, x and y. So this is our replacements for flag 0 and flag 1 used in the previous program. So after the initialization, we spawn two threads. In each thread, we first write to some location the value 1, and then read from the opposite location. And after that, we check if the value we read is 0, then we run critical sections. So apparently, we expect that this locking also works, and this like simplified version of Dekker's lock. And why it works? Because we expect that only outcomes allowed for A and B are either A being equal to 0, B being equal to 1, or A being equal to 1, B being equal to 0, or A being equal to 1, B being equal to 1. So how we get the first result? To get the first result, we first execute the left thread, then the right one. To get the second result, we do opposite. First execute the second thread, then the first one. And to get the result A being equal to 1, B being equal to 1, we first execute the first instructions on each thread, and then perform the reads. So there is no interleaving of these threads, which will lead to result A being equal to 0, B being equal to 0. Okay, let's once again check it on Anton's laptop. Here we have, once again, two threads. So now the program is even smaller. It's more or less the same as it was on the previous slide. So in the thread 1, we just write to location x, then read from y. In the second thread, we write to 1, then read from x. We once again do a loop, which tries to catch something which is different from what we expect. So namely, we iterate while while we didn't get the case A being equal to 0 and B being equal to 0. So once again, if we compile this program with GCC and execute, we'll get that we'll have some strange result after 15,000 iterations. You may get it faster or maybe after more iterations, but it's actually pretty easy to get this behavior on any laptop you have with ARM or x86. Let's see what's going on there. So to do that, first let's take a look at assembly of this program, which was produced by G++. So first, these three lines, they represent the thread 2, where we first write 1 to y, then read from location x to register EIX, and then from EIX we write it to location b. So everything is like in the program, except that we spilled the move from one location to another to two moves, because in x86 this is what you have to do. Then you access two memory locations. But now let's take a look that's going on with thread 1. So here we'll see that first we read from location y to register EAX, then write 1 to location x, and then move the value from EAX to A. So essentially, here the compiler did the swap between the read and write instructions. So the compiler is allowed to do so because it can deduce that x and y are different locations in memory, so why not to reorder them? However, this is what breaks the invariance which we had programmed, right? Yeah, so we have to do something about that. What we could do? To forbid this reordering. To forbid the reordering, we may insert empty assembly inline instructions, this one and this one, and if we will take a look at the assembly code which we get, there will be no reordering. However, even though we forbid the compiler to reorder these instructions, if we compile the program and execute, we still can get this strange behavior, and actually in this case, for some reason, we got it even faster than in the previous case, right? So now it happens after 800 iterations of the test, not 15,000. And the reason for that is because x86 and actually ARM as well may perform on x86. It's like more or less standardized terminology, may buffer the reads. Oh, sorry, the writes. And to explain what's going on, I'll use some mathematical representation of the architecture. So here, instead of just having like plain connections between the CPUs and memory, there is something in between. This red box, it's a write buffer, and it works like that. If CPU wants to write something to memory, it first issues a write request which stays in this write buffer, and then it's eventually propagated to memory. And if CPU wants to read from some location, then it first checks the buffer if there is something new written by the CPU itself, and if there is nothing, then it goes to memory. So then to get the strange behavior A equal to 0, B equal to 0, we can have such an execution in this model. So first we execute this write, and the corresponding request now in the write buffer, but memory still assigns x and y to 0. So then the second thread could execute the first instruction and put the corresponding request to the its write buffer. Then the reads performed, so the left thread executes this read from y. There is nothing in its write buffer which assigns anything to y, so it goes to memory and gets the value 0. The same happens in the second thread. So this is how we got the result A being equal to 0, B being equal to 0. Then in the end of program execution, the buffers could be flushed, but it's too late for the reads to get the proper values. So anyway, you could forbid this behavior on x86 as well. For that, you need to insert not empty assembly instruction, but in this case mfence. So if we'll take a look at the assembly now, there will be special assembly instruction mfence, which stands for memory fence, which will forbid the behavior from happening because it will force the buffers to be flushed before anything after the fence could be executed. So now if we run the program, then if everything is fine with your CPU, then you shouldn't get the outcome. So I had to interrupt the execution of the program for it to stop. So any question at this point?
how performance changes.
Yeah, so obviously then you forbid some compiler optimizations, then you can have your performance may be reduced for obvious reasons. Now you cannot do some optimizations, right? So for example, the ordering of the instructions. If you insert these memory fence instructions in your code, then you also have some performance degradation, and later in the presentation we'll see how much. But yeah, obviously it's expensive. Yeah, if you insert these instructions between every two instructions in your program, then you'll guarantee sequential consistency, but it's too expensive.
Why this behavior depends on optimizations that you use in -0.2 or not?
For sure. So let's get back to this code where we get the reordering. Yeah, so it's here. The reordering. If I execute without -0.2, then there'll be no reordering. Yeah, and actually I had to do some tricks for this program to force compiler to do the reordering. I mean, it's not even true that I forced it, because I guess the compiler could produce the code without reordering. But anyway, for example, as we can see in the thread 2, there is no reordering. However, there is some reordering in thread 1. Yeah, and actually, if you're interested to get this, this is why there is like cout flush in the program, because when I was trying to get the reordering, I realized that I need to insert any function call in the beginning of the thread execution, and it should be something which doesn't affect the program. So in this case, we don't do any writes to the standard output before we execute these instructions. So it should like do nothing, but still there is some function call, and for reason I don't know, G++ does the reordering here in this case.
Yeah, actually, I have one question.
Okay.
Why we do not consider the loop in the main function itself, like concurrent reading from the shared memory? Why we don't put the main loop on the lock to like other thread?
Yeah, I mean, we could do that, but still we could get the result without any interactions. So I guess this join should do the trick. So usually things like join, they have the memory fences inside their implementation, so it should be fine in this regard. Any other question? Okay, so yeah. So as you can see, sequential consistency introduced by Leslie Lamport does not express real concurrent behaviors, which you can see on like real CPUs nowadays with real compilers. And like both CPU and compilers are the ones to blame for like these strange behaviors. And these strange behaviors, which are non-sequentially consistent, they are called weak behaviors. And memory models or semantics of program languages or CPUs which allow weak behaviors, they are called weak memory models. And like all real systems nowadays, they have weak memory models, so they don't force sequential consistency. Yeah. Okay, one other small example. So here, like before, the example we had, it's called store buffering, because we had to get the weak behavior, we had to buffer the writes to the memory or stores. This is like the opposite example. So here, once again, we have like two shared locations, X and Y, which are initially initialized by 0. But now we first do reads and then do writes. So obviously we could get result A being equal to 0, B being equal to 0. For that we just execute the reads and then the writes, right? Also in sequential consistency we could get A being equal to 0, B being equal to 1. For that we first execute the left thread and then the right one. The vice versa is also true. If we want to get B being equal to 0, then we just execute the the right thread and then the left thread. However, we shouldn't be able to get the result A being equal to 1, B being equal to 1. At least it's forbidden in sequential consistency. It's forbidden not only in sequential consistency, it's also forbidden by x86 architecture. However, it is allowed by ARM. So potentially if you have like Mac laptops with M1 or M2 CPUs inside, like this one, then potentially you could get this result A being equal to B being equal to 1 after executing this program, because the specification of our platform allows it. So let's take a look how we could get this result in some mathematical model called ARMv8 POP, which explained like all the version of ARMv8 memory model. So the idea is here that instead of like executing instruction in one thread line by line, we are allowed to execute instructions out of order. So here we use the gray boxes to denote the instructions which are not executed yet. Then we'll use yellow boxes to denote the instructions which are partially executed. So here the right thread started executing the read and it issued the read request. So currently it's in like request buffer, which is kind of similar to the write buffers we saw in x86 model. And we will use like the green boxes to denote the instructions which are fully executed. So the write instruction in the right thread send the write request to write 1 to X in the memory, and so it issued the request and doesn't wait for any response, so it's executed. Unlike the read instruction, which waits for the value to be written to register B. So once these requests are in the request buffer, the CPU, or rather the mathematical model which explains its behaviors, may realize that X and Y are different locations. So these requests are independent, and so they might be reordered inside of the request buffer. So after they reordered, we can propagate the write request to main memory, and it will update the value there. So now we'll get to execution on the left thread. So it may issue the write request even before it started to execution the read instruction. So now this write request may propagate to memory. After that, the read request may get the value 1. So now the only instruction left to be executed is the read. So this is how we can get the execution, the outcome A being equal to 1, B being equal to 1. So there are different memory models for different CPU architectures. Among them, most important ones, x86, IBM Power, and ARMv8. There is also like RISC, which is RISC-V, which is very popular nowadays. And actually, it has a memory model which very close to ARMv8. On top, one of memory models which are specified in the architecture manuals, there is compilers, which, as we saw, could do some tricks, which also may change behavior of your concurrent program. Then there are standards of the languages, which have to take into account both compilers and CPU architectures. Like, for example, if you want to compile C++ efficiently to ARM, then C++ should allow more weak behaviors or equal number of weak behaviors as ARM, as we will see a bit later. And then in the end, there are software developers who wants to use these specifications. Yeah, so there are like many things which affect memory models used by software developers. So now I want to get to the second section of the talk and to talk about requirements which we impose on memory models. And actually, I prefer to divide memory models to two groups. Then I speak about requirements to them. Obviously, it's hardware and programming language memory models. So then we speak about hardware memory models, the things which are specified in architecture textbooks. We want them to be precise and in a sense that they describe real CPUs. So if there is something which may happen in real life, we want it to be allowed by formal specification of the architecture. Also, hardware memory models designed in a way that if, like next year, Intel decides or AMD decides to make some new optimizations which wasn't there in their older CPUs, then it would be good if programmers would not need to rewrite their programs because the CPUs changed, right? So the specification should be weak enough to allow these potential future optimizations. And the third requirement is that, as we saw on the previous slide, we want to be able to build this tower of memory models. So we want to provide reasonable guarantees to compilers and to programming languages to build on top. Yeah, so this is essentially the requirements for hardware memory models. And I should say that the existing memory models for hardware, they are solving these problems, and there is not much left in terms of like scientific research. So still there is like a lot of work being done, improving them, considering more and more parts of CPUs. But still it's like more or less stable area nowadays. Programming languages, memory models, they are much more interesting in my opinion. So let's get to them. What we want from these memory models is that we want to allow the compilers to do their job. So the memory models should allow compiler optimizations. So they should take into account their changes to programs. They also should provide efficient compilation schemes to hardware. So like, for example, if you compile C++ to x86 ARM and IBM Power, then the memory model of C++ should take this into account. And also, ideally, programming language memory models should allow like easy non-expert mode, which we'll dive into more. I guess this is like the most vague statement on this slide, but still the idea is that if you like write good programs good enough, then you shouldn't get very strange behaviors, right? So ideally, if you like write like good enough programs, then you get sequential consistency. Okay, so now we'll discuss these 3 requirements imposed on programming language memory models in more detail. So first of all, compiler optimizations. So suppose we have this store buffering program, which we saw in the very beginning of the talk. And suppose we want to allow this reordering, the one which was performed by GCC, as we saw. So in the end, after the optimization, we get the program like this, right? So it means, so if we want this optimization to be correct in our memory model, we need the following statement to be true. We want all behaviors which are allowed for this program to be also allowed for this one, right? So if our text manual says that there are like only 3 executions allowed for this program and 4 executions allowed for this one, then the optimization is wrong, right? So after the optimization, we get more behaviors. So here we use these semantic brackets to denote the set of outcomes allowed by this program and correspondingly this one. And so we require these sets to be included one in the other. The second requirement I said is like efficiency of compilation to hardware. So for example, suppose we designed a new language and we decided that we don't want to deal with this old nonsense of weak memory and want to have sequential consistency. And yeah, let's say we want to compile our new shiny language to 86. Then to enforce this sequential consistency, as we saw with store buffering, we'll have to first insert these memory fences. So in my terminology, this is compilation is not like fully efficient, right? Because we imposing these things which slow down our program. So some languages may allow it. Some languages want to be as close to hardware as possible, for example, as C and C++. So yeah, so this is like the reason why C and C++ cannot have sequential consistent memory model. And the third requirement I said was that ideally programming language memory model should have easy non-expert mode. And essentially statement is like nice programs behave nicely. So let's discuss it a bit in more detail. So essentially we want to say if there is no data races in our programs, if there are no race conditions, then only outcomes allowed by sequential consistency are allowed for the program. Okay, yeah, I have like one question for you. So could anyone explain what is a data race or race condition? Anyone?
The data that makes behavior undefinable, like indeterminate. So I think there will be multiple definitions. So
yeah, this is good. Yeah.
Basically, it's when it leads to indirect behavior. Because, for example, if we are modifying atomic variables for different jets and having different results, it's still not a data race, but we have different results, but we are expecting it. So when this behavior is not as expected, then we say it is the data race accuracy. But might be.
Yeah. Okay. So I would yeah. Let's try to define a bit more precisely. So like data race for me is a situation. Then you have like two accesses to the same memory location. One of the accesses is write. The other one could be write or read. And these accesses they could like be executed simultaneously in a sense, right? So concurrently. Like in different contexts, like people like to define the data races slightly differently, right? So for example, like I guess a lot of you heard about Java memory model, and in Java memory model, like the data race is defined with the sum happens before relation, which is a part of the model, and I guess I'll need like 15 or 20 minutes to explain the details of Java memory model and the definition of happens before there to define the data race. Okay. Ideally, actually, what we would like to have from the memory model, it's even like a bit stronger claim, saying that if there are no data races in sequential consistency executions, and actually like data races in terms of sequential consistency, then there are only sequential consistent behaviors. So what does it mean for execution in sequential consistency to not have data races? So as I said, data race is like two concurrent accesses to the same location, one of which is write. So in sequential consistency, when we have a situation, then like two different accesses could be executed simultaneously, right? If we execute like step by step in different threads. It's a situation, then we executed like, for example, two threads up to two instructions, and these two instructions exactly in conflict, right? So like one of them is write to location X, the other one is read from X. And yeah, so like the definition is like not that hard to explain. You don't need to understand like Java memory model or definition of happens before there to understand what is data race in sequential consistency. And so, yeah, so why this? Yeah, so by the way, these conditions like usually called data race freedom guarantee, and why the formulation in this sense is good, because like if you are writing like good enough programs, that the only thing you have to know is sequential consistency. So there is nothing language specific or memory model specific in this definition, right? So there is like no happens before or something like that. And then you get only sequentially consistent behaviors, which is also quite easy. So let's take a look at this program. So here we have something which is very close to like load buffer, an example which we had like a couple slides before. So once again, we have like first reads and then writes. However, now these writes are the conditional one. So we have some conditions here. Let's try to execute this program in sequential consistency. Once again, if we have x and y being equal to 0. So we start with executing either this read or this read, right? We anyway get the value 0 here if we perform this read. So then there is no way we'll yeah, I don't know. Oh, okay. So anyway, if we execute this instruction, then there is no way the write 1 to y. So then it means that the only outcome we could get for b is also 0. So there is no way to write anything to x. So the only execution of this program in sequential consistency results in a being equal to b being equal to 0, right? Okay, are there any data races in sequentially consistent executions here?
Could be. If you used code.
No. We don't know about these fancy things like volatile. We just execute a
volatile if construction. Like previously there was like conditional dependency, or how what is called. So like previously there was like a guarantee, but not anymore. Like there is like hardware guarantee as far as I know, but for example for the C++ languages, like we built the minds anyway.
Yeah. So you know a lot, and like I guess you're like trying to do something too clever for this statement, right? So actually there are no data races in sequentially consistent execution of this program, right? Because there is no situation, then we could execute this instruction and this instruction concurrently, right? There is no situation, then we like could make one step or another at the same state of the program execution. The same goes for accesses to y. So actually there is no data races in sequentially consistent execution of this program. So we expect that the only outcomes allowed is the ones allowed for sequentially consistent executions. And actually it's a being equal to b being equal to 0. However, C++ memory model allows to get here a being equal to b being equal to 1. Yeah? And yeah, the reason why I used the red box, because this is not what we would like to have, right? So there is some problem in C++ memory model which we would like to solve. Yeah, and actually we'll discuss it a bit more detail why C++ memory model has this problem. So any questions up to this point?
How is it possible? Because it's never come to the why.
No. Okay, yeah, it's a very good question. How it's possible? The thing is that it's impossible in a sense that any reasonable C++ compiler which will take this program won't produce you anything which could be executed on like reasonable architecture, which will give you this result. However, the specification of C++ language allows this outcome. So this is like the problem of specification. And like the whole like research area which I'm presenting in this talk is about like fixing these specifications, and then potentially fixing the compilers, and maybe like reporting some like desires or bugs to like CPU architectures as well. But like the like main focus in the very beginning, we try to come up with like proper formalization of things which are going on. Okay, any other question at this point? Okay, good. So such outcome, it has actually like a special name. It's called out of thin air, or UTA, or OTA. Yeah, and it's considered to be harmful for specification to allow such things. So now let's discuss the existing programming language memory models in the context of the requirements we just introduced. So I start with like 3 most popular and well-known memory models for programming language out there. It's Sequential Consistency Java memory model and C++ memory model. And we consider how good are they regarding the 3 requirements we had: compiler optimizations, efficiency compilation to hardware, and DRF, or absence of out of thin air values. So like regarding sequential consistency, compilation optimizations, some allowed, some not. So if we take a look at this list, there are like many optimizations which are allowed. You don't have to go through the whole list. So in a sense, I just wanted to show that there are just like 2 things in this list which are disallowed. There are actually many more. You could like divide the optimization slightly different way, but we'll use this just to compare it to some other, actually to Java memory model. Yeah, so we don't allow reordering of normal memory accesses, but we allow quite a lot of other stuff.
This normal memory access.
This is what exactly we just had. Like if you have just normal access without like special annotation, like in C++ special annotations are like atomics, in Java it's volatile or var handlers. Like you would like to be able to reorder normal memory accesses. Yeah. In sequential consistency, they could not be reordered. It's unsound optimization, as we just saw, right? Like when GCC reordered accesses in Dekker's lock, we got something which was out of sequential consistency, right? Okay. Right. So as we saw, some optimizations are disallowed by sequential consistency, but maybe they are not that important, right? So there was some paper which tried to check how much we lose by forbidding optimizations which break sequential consistency. And yeah, to test that, the authors took LLVM, and first they just turn off the optimizations breaking sequential consistency, and on some benchmark, it's not that important now which one, it showed like average slowdown of 34%, so not that much, right? But then instead of just turning off the optimizations, the authors decided to modify the optimizations to preserve sequential consistency, right? And after that, they managed to get with like 5.5% of slowdown. So like the point of this is that you lose something. However, it might be not that much, although you still don't get the sequential consistency, right? Because still hardware could get your program to weak behaviors. With the other drawback of this approach is that you'll have to modify existing compilers, and it's a lot of it's a lot of work, and yeah, so this is not what like most of at least compiler developers would like to do, right? Regarding Java memory model, surprisingly, there are some problems with compiler optimizations going even further than in sequential consistency. Like, for example, the redundant read after read elimination, it used to be broken. Actually, I'm not sure what's the state currently, but this was like a very important bug in a sense that there was like Java memory model specification which disallowed the optimization, which was actually done by the main JVM implementation in Hotspot. There was a bug regarding to the specification, because Hotspot did the optimization. Then apart from this, there are some other things which are surprisingly allowed by sequential consistency, but not by Java memory model. Okay, like regarding C++ and compiler optimizations, the thing is that C++ memory model is more or less fine. It allows quite a lot, but as we will see, it will strike C++. Then we'll discuss other, actually the last column. Okay, so like regarding efficiency of compilation to hardware, sequential consistent has like a very bad situation. So let's discuss. To check how much it will be to get sequentially consistent behaviors on like modern architectures, colleagues decided to do the following. They decided to modify JVM in some way, which will enforce all programs to behave like in sequentially consistent. And what they did, so they used the claim the Java memory model has, that it guarantees data race freedom. So the claim in Java memory model could be simplified to this statement, saying that if all locations which could be used concurrently, if they all marked as volatile ones, it will say that it will lead to having no data races in terms of Java memory model. Then by data race freedom guarantee, we have only a C semantics for the programs. So what the colleagues did, they essentially modified the JVM to assign volatile to each such accesses. Actually, they did some like clever tricks regarding arrays and etc., etc. But it's if you want more details, please read the corresponding papers. But yeah, the idea is that there were some good engineers who tried to modify JVM to have these volatile accesses to everything which is shared. And then they tested these in like a couple sets of benchmarks. So they used the Dakapa benchmark is set of Java programs, like big Java programs, including like Gton, Java implementation of Python, and yeah, sorry, I don't remember more, but yeah, like big programs in Java. And also they used benchmarks for Apache Spark, like performance tests. So, and then they measured slowdown on like different servers. So first they tested on x86 and then on two like ARM servers, like with many cores. As far as I remember, they were like from Huawei, but I'm not sure. Yeah, so what it showed that on x86, the slowdown on average was around 28% for the Kappa benchmark and 79% for Spark, and like maximum slowdown for some programs was even bigger. So yeah, this I guess for many applications it's not that bad, but yeah, for many others it's like too much of slowdown, right? If we go with ARM, which actually has like weaker memory model, which allows more behaviors, the slowdown is like much more. So here I even have like infinity, because in the paper the authors stated something like 5,000% slowdown or something like that. So it was like very big. So as you can see, like enforcing sequential consistency in like real life for like most of the applications is something undesirable because it's like too much slowdown. Okay, so as we discussed, efficiency of compilation to hardware is not that good for sequential consistency. For Java and like C++, the situation is much better. Actually, as you can see, for Java I used like neutral phase, and the reason for that because like there is a very interesting situation that like like the current implementation of hotspot for IBM Power processors, it's even like too efficient. Meaning that they don't use enough fences, and it like potentially it could lead to behaviors on hotspot which are not allowed by the specification of Java memory model, and it's like known bug. Then we discussed it with like a member of Java standardization committee. He said that yeah, it's like well-known thing, but they don't want to fix it. They don't want to introduce more memory fences because it will slow down the existing programs, so they don't care about that. Okay, so now let's discuss the last component, this absence of out of thin air values in DRF. So in sequential consistency, it's like very good situation, obviously, because the only behaviors we get are sequentially consistent. In Java, it's considered to be good in a sense that, like most, it's considered to be true that Java memory model doesn't have out of thin air. However, there are some discussions that there are problems in Java memory model still. And actually, the thing is that the way Java memory model solves this problem is actually a bit problematic, and because of that, Java memory model has some drawbacks, and actually like relatively hard to understand comparing for other memory models. But if we discuss C++ memory model, then we'll see that the situation is the worst among these three. And as we already saw, the out of thin air example, and this is like the main problem with C++ memory model, which the community tries to solve at least for last 10 years. Yeah, and now let's take a closer look what's the problem actually. So we already saw this program. As we discussed, there is no data races in sequentially consistent executions of this program. So there shouldn't be anything except for A being equal to B being equal to 0. But now let's consider like very similar program. The only difference we have here is that in the left thread we don't have a control dependency, right? So now in the right thread there is still control dependency, there is still if, but in the left we don't have anything. And now let's see how the C++ memory model formalizes possible behaviors of programs. So it uses so-called execution graphs. So this is like one of the execution graphs corresponding to this program. So in the graphs, the vertices are like different memory accesses. So here we have, in this execution, we have 3 memory accesses, like 2 reads corresponding to these 2 read instructions, and one write corresponding to this write instruction. Edges in the graphs are different relations among the memory accesses. So here we have only one type of edge, PO. PO here stands for program order. So here, these 2 accesses, they correspond to these threads, so that's why there is program order between them. And the right thread in this execution, for B it gets 0. So there is nothing to be executed afterwards. So there is only one access. Yeah, and obviously this execution graph corresponds to outcome A being equal to 0, being equal to 0. The other graph corresponding to this outcome already has like 2 memory accesses in the right thread, also ordered by program order. There is another edge going from this right. So this view. This Rx. Yeah. Okay. So read stands for read. R stands for read. X. This is the name of the location which the access reads from, right? This one. So here we have X and Y, which are shared locations. So this is why we have here location X. And 0 stands for the value which we got, then we executed the corresponding instruction. Yeah, thank you for the question. Yeah, so the second execution here, so as I said, there is one other type of edge, this green one, read from. This RF stands for read from. And actually it relates the writes with the reads if the read reads the value written by this write. Yeah? So if we have this edge between read and write, then they should access the same location and read and write the same value. Okay, and the third graph for this program corresponds to execution A being equal to 1, B being equal to 1. So here we have this Rx1, which reads from Wx1, right? Yeah, and so this is like execution graph, which is allowed for this program in C++ memory model. So how we construct these execution graphs? First, for each thread, we construct potential sequence of memory accesses. Then we combine these sequences in the graphs. We write reads from edges, so that for each read there is a corresponding write it reads from.
Like the last graph.
Yeah. What do you mean? It's possible to have a cycle in the graph.
This graph, it's impossible because I read the x1, I write it to the y1, then
yeah,
because of this is the cause of itself. It's
yeah, causality cycle. Yeah. So this thing is causality cycle. Yes. And actually it's fine. Okay. And we'll see how. Actually, it's rather easy. So once again, we have like C++ memory model being like some mathematical formalization of the outcomes allowed for the program, right? So we can construct this graph, and it's allowed by C++. So your question is, how could it be allowed? How could we get such a behavior? Suppose. Yeah. Yeah. Obviously we have like. Yeah, obviously we have Back to the Future situation here. Okay, so once again, we want C++ to allow compiler optimizations, right? A compiler could take a look at the left thread and reorder these two instructions. No, these two. There is no if in the left thread. And if it does so, then the outcome will be allowed for optimized program, right? But we want to construct mathematics such in a way that it allows the behavior for the initial program if they allowed for optimized one, right? So that's why we allow such cycles. But you're right. Cycles like that in like pure and RF, this is like the most complicated part of weak memory models. And some memory models like x86, they disallow these cycles, but ARM, for example, allows. So even if compiler does nothing, and like for example, if we write this code on ARM assembly and execute, we could get this outcome. We could still get a being equal to 1. And the reason, as we discussed, like in the second example or the third one, like half an hour ago, for ARM, yeah, because ARM, I mean, like in a sense, right? In ARM, it's just allowed to execute some instructions out of order. You could think about it as reorderings, and like many people think about weak memory being like being only about reorderings. Actually, it's not true. I don't think I have the example in my slides, but some weak behaviors couldn't be explained by reorderings. It requires something more, but most of them, yes, most of them could be explained by reorderings. Okay, any more questions here?
C6 that's allow.
And as we saw the first example, it allows to reorder like write with the following read, but it does not allow this reordering. It does not allow to reorder read with the following write. Yeah.
Understand if C++ model allows reorderings, why in this graph the O edge is directed at all? I mean,
why is there, right?
why it is directed? There is an error.
Okay. Once again, this is like some formalization which we would like to have. We would like to have some program order, which is like a total order on the whole sequence of accesses to each graph. As we will see, you can ignore some of these edges. It's not that you have to like respect them all, right? It's just like some simple part to be there to like. Actually, it's like very important for mathematics of this. Yeah, but it's there. Yeah. So once you constructed the execution graphs, there might be some inconsistencies, but then inconsistencies in terms of the memory model. But then there are like a bunch of axioms for each memory model. They are different, which says that usually some cycles are disallowed. Yeah, what I didn't say, but I wrote on the slide here. So memory models which do the things like that uses the execution graphs and then like a list of axioms to forbid some executions. They are called declarative or axiomatic memory models. And yeah, like more or less they all use these like general structure. So for example, all hardware memory models, they have quite established and like reasonably good axiomatic memory models. But as we will see, for programming languages is not like good enough. Yeah, so let's take a look at one of the axioms. So here it says that PO union RF relation is acyclic. Actually not RF, but like some subset of RF. So some RF edges are important for us, others not. So if you know something about Java memory model, then this RF preserved set is something like synchronization or synchronized with in Java. But the idea is that you could like take like some edges in important, some not, like depending on situation. So in this graph there is like no difference between these two RF edges, but like for example, if I marked the X location is volatile in Java, then this RF edge would be something important. But if you don't know about volatiles in Java memory model, then just think that some edges could be important and some not, right? So the axioms of memory model looks like that. Like some combination of relations should be acyclic, right? So now take a look at the programs we already saw. So this is this infamous out of thin air example which we discussed in C++ memory model, right, with control dependencies in 2 threads, and the version of it without control dependency on the left thread, which we discussed just a slide before, right? For both of these programs, we could write the same execution graph with accesses to read accesses to x and y, accesses to y and x write ones, and with cycle in PO and RF relations, right? Yeah, as I said, we first construct these all possible executions for the program, then we filter them with like a list of axioms. So if we want to forbid this execution graph at all, then we'll forbid it for this program, right? In C++ memory, but I mean, forbid the graph. Return is like low-level explanation which couldn't be used on this level. Yeah, so if we forbid this graph, because we would like to forbid this graph for this program, right? Because we think it's nonsense. For this program, we don't want to forbid the same graph. And the reason for that, because if we execute it on ARM, then we could get this behavior. And so if we want to efficiently compile C++ programs to ARM, in C++ memory model, we should also allow this execution, right? Okay, what could we do? We could add some auxiliary edges to the graph, right? So we could take into account that there are control dependencies, the ones we discussed, right? So now, in the graph for the first program, we have this control dependency on the right thread, but for the second one, we have a control dependency on both threads, right? Okay, now the problem is solved, right? We can just say that C++ should disallow cycles of the form control, read from, control, read from, right? Yeah, so and then for these 2 programs, we solve the problem, and yeah, there's nothing much to do, right? However, there is a third program. And in this program, what we have in the left thread, we also have control dependency from read to write, yes, but we could also construct the same graph here. But what's the difference between this thread and this one? Who could say? Yeah, yeah. So this third program could be optimized to the first one, right? Yeah. Okay. But what's the difference in terms of these edges, right? One could say that here we have like a fake control dependency, right? So fake control dependency could be eliminated by compiler. It couldn't be by CPU, and usually CPU doesn't do that. So this approach with having like extra dependency edges, it works perfectly fine for hardware. And this is how it solves the problem there. However, it doesn't solve the problem for programming languages, because we would like to take into account optimizations like this, right? Which takes the third program and makes it the first one. So now we need some way to distinguish between fake and real dependencies. And this is actually the main challenge. So if we could say which dependency is fake and which is not, then we solve out of thin air problem. But that's not that easy, right? Yeah. And actually, currently the Research Society still didn't come up with like a solution which is considered to be like the complete solution. So still, as I said, this like very known problem with out thin air executions for like many years, at least. Yeah, so like for example, Java memory model paper is from dates 2005, and Java memory model wanted to solve out of thin air problem. So it actually people were working on out of thin air at least like a couple years before publishing this paper. So it's fair to say that at least for 20 years, Research Society works on this out of thin air problem, but still there is no definition out of thin air. So still there's like a bunch of examples of which yeah, there is no formal definition. So like for example, if there would be someone from C++ standardization committee, they could say, no, there is like no problem in C++ memory model. This like claim that there is some problem with out of thin air in C++ is wrong. And they would be like it could be considered kind of true, because in the like C++ standard, there is like explicit statement saying that, okay, first you do these axioms, and then there should be no out of thin air. But there is no definition of out of thin air. Yeah. So there are like different solutions for the problem, and like one of them, which is considered to be like likely to be adopted by like many languages, was proposed by my colleagues in their like 2017 paper. But actually, the idea was there for like some years, and the idea was just to forbid all PRF cycles, right? RC11, it stands for repaired C11 memory model. C11 because yeah, C and C++, they have like similar memory model, which was introduced in 2011, and actually there were like minor changes in the like 14, 17 standards, but like the main problem is still there. Yeah, so the colleagues proposed to forbid the PRF cycles. So it means that now we couldn't get the behavior allowed by ARM. So it means that we couldn't get the efficiency, like fully efficient compilation to ARM. And some compiler optimizations are now disallowed. But instead we get like very simple semantics, which is obviously disallows out of thin air outcomes. Okay, let's try to discuss something regarding these PRF cycles. So interestingly enough, if you want to forbid these PRF cycles, it means that you need to respect pure this program order edges, which goes from reads to writes. So this is like mathematical notation, which essentially denotes pure edges which goes from reads to writes. To respect meaning that if we'll enforce this program order to be, if we disallow all these reorderings, then we'll forbid PRF cycles. Yeah, so, and why is that? Suppose we have a cycle of pure and RF edges, right? Like this. Yeah, so like we have some alternating pure RF, then we may have like a couple of pure edges. We couldn't have like two RFs right after another, one after another, because RF edges, they go from write to read, and then we would have to go once again from write to read, but like reads and writes are different memory accesses, so there couldn't be like two RF edges one after another. So some of the RF edges, they also coincide with program order. If it's like internal read, if like for example you had like a write and read in the same thread, and this read from this write, then this RF edge could coincide with pure. Otherwise, if RF does not coincide with pure, then it's essentially RF minus pure edge, or like external RF edge. So yeah, if we consider this, and as I said before, program order is something which totally orders accesses to the same thread, so it's transitive, and we could replace some of the edges with like bigger ones, like this, right? So now we have a cycle on pure and RF minus pure edges, and now if we consider where these RF and pure edges goes from, they go from write to read. So these read minus pure edges, they are always important in the sense that since they go from one thread to another, they couldn't be broken by any like reordering or something like that, and actually they're respected by all hardware. So the only question, if we want to disallow this cycle, is how to respect this ordering between reads and writes. how to forbid the reordering of reads with following writes. So what we need to do, we need to restrict compiler optimizations from performing these reorderings, and also we need to probably put a fence between each write and read, right? Yeah, and actually now we'll dive a bit into why this approach is better for languages like C++ regarding their memory model than for Java. So, and the reason for that is that in C++ there is undefined behavior. So, suppose you have a program like this, and suppose like both locations here, data and f, are just like normal ints in terms of C++. Then in Java, you would get a result that fine, you may get some like strange behavior. So here, let's explain the program a bit. So here we have like data we prepared, then we have some flag, meaning that data is already prepared. Then we are like busy waiting for the flag being set, and then we print the data. So here we would like to have the only outcome is 42 being printed, right? In Java, yeah, actually, it's not the case in the memory model. Why? Because like there is no these two accesses could be reordered, right? So you could get the outcome, for example, 0, like Java. In C++, this program does not have behavior. Actually has undefined behavior because there is a race on like normal locations. So if you mark data and f as just normal ifs, then there is undefined behavior. So on Java, it's not a problem. In Java, you could have races on like normal memory locations. So to fix this problem, you need to mark this f as an atomic, and actually mark accesses as like special accesses as like release and acquire access. These accesses essentially will, like once you compile it to hardware, they'll essentially introduce memory fences. So like release access essentially introduce a memory fence before the write instruction, and the acquire access essentially introduce a fence after the read instruction. So you will have, in this case, you could think as you have a program with fence between these two instructions and a fence between these two instructions. So then you won't be able to get any strange behavior for this program, and the problem will be solved. So the difference between C++ and Java is that, like in Java, you could also have like special locations, which are marked as volatile ones. In C++, it's special atomic locations are atomic ones. Data races on like normal types just give you weak guarantees. On Java. In C++, it leads to undefined behavior, right? So, and if you want to have like usual access with arrays on Java, you could have like normal access on like normal int. In C++, if you don't want to provide any synchronization, like in this case, but still would like to have defined behavior, not undefined behavior, you would have to mark your location as atomic one and accesses as a relaxed one. These relaxed accesses are compiled to hardware without any fences, but specification at least provides some guarantees about them. Yeah, so actually these accesses, this is what could lead to out of thin air, right? So this is what we will need to fix somehow if we would like to forbid out of thin air. So yeah, essentially, if your language has this undefined behavior of normal accesses, like C++, then you don't have to care about all accesses, you have to care only about atomic accesses. Essentially it leads to, if you want to forbid these PRF cycles in C++, you need to respect this RPO to write on atomics only. And the set is much smaller than like all accesses. So colleagues showed that if you want to enforce this order in LLVM, you would have to obviously restrict compiler optimizations. And interestingly enough, in LLVM, you have to do nothing. LLVM already doesn't reorder such atomic accesses. And regarding the compilation to hardware on x86, you don't need to do anything, once again, because x86 does not reorder such accesses. On ARM, you would have to do something, and actually they proposed like 5 or 6 different schemes how could you do that. So, like for example, in ARM there is like lightweight fence which specifically designed to forbid these orderings, but interestingly enough, they showed that it's better to just introduce bogus conditional branch between these relaxed accesses, and then you force the order. I mean, it's obviously forces the order, but it's makes less performance problems than using the lightweight fence. And then they tested on like a number of like big programs, and they showed that on obviously on x86 there is like no price to pay. You don't need to modify LLVM. You don't need to do anything with assembly. You don't need to insert anything. In ARM, you do need to do something. And interestingly enough, on average, it led to slowdown of 0%. And in worst case, it was around 6.3% reduce of performance. So what does it mean? It means that for many languages, like, for example, Python or Scala, or I don't know, anything except for like C++ and C and maybe Rust, probably you could just get away with like simpler semantics, which has obviously no out-of-thin air problems, because yeah, the price is like relatively small. On average, nothing you have to pay. For C++, it could be still problematic because people would like to be able to write as fast as possible on bare bone, right? So, in a sense, preserving this read point pure to a right order is good for atomics, but what about Java? So, yeah, the idea is that if you don't want to preserve this order between reads and writes, instead you could preserve these syntactic dependencies, like we did with hardware, right? So you could forget about this fake word and consider any like dependencies as like true ones. So the colleagues modified LLVM to do so. They took 46 optimizations, modified 35 of them to not break dependencies and turned off hours. And on some, like once again, big benchmark, they showed that average slowdown on ARM was just 3.1%, and at max it was around 20%. So once again, quite a lot for one languages and not that much for others. Yeah, so there are other memory models which were presented by research community, and some of them, in like design of some of them, I participated. So these memory models like solve more problems of like the main idea behind these three is that they introduce their own notion of fake and the real dependencies. These like the main drawback of these models that they are much more complicated and different from what we have in programming language standards nowadays. But yeah, unfortunately, I don't have time to talk about them in detail. So the other column, which I consider also important for memory model, is how hard it to be explained. So the good thing about this C11 memory model, which we just discussed, is that it's like relatively simple, especially if you already know like C++ or Java memory model. The drawback, as we saw, that there are still some performance issues comparing to the existing C++ memory model. you could probably do something more if you want, but then it will lead to like harder memory models, which are more complicated and understand by like a couple dozen of people. Yeah. So actually, it was faster than I thought. Anyway, so the takeaway of this talk is that the memory models of mainstream languages have major drawbacks, but still there are some existing solutions which compromise on different things. So, like, if you're developing a language which is not Rust or C++, probably you could get away with a model like C11 or something like that. And then, yeah, if you allow undefined behavior, you could do quite a lot, even in terms of memory models. So, yeah, if you want to leave your feedback about this talk, you could do it with this QR code. If you have any questions, I'll be happy to answer. Rust memory model is not developed yet. So currently the web page says that, yeah, so essentially there is no memory model. My colleagues are actually kind of working on that. And like, for example, this promising memory model, it was a part of like big grant which involved some people from Rust. Yeah, and they, like, using these models, they verified some like internal implementation of libraries in Rust. But essentially, once you'll have like a memory model for C++, most likely you'll have also for Rust. So they like go like hand to hand in a sense.
Has same guarantees like C++ memory model?
I mean, it's not officially stated, but this is something which you could assume. Yeah. One other important thing about Rust. So in Rust, the type system does not allow you to do the like shared memory concurrency, right? Because you cannot have like concurrent accesses to the same location. So actually, you need a memory model only for unsafe part of Rust. But you still do need it because in unsafe part of Rust, like many like primitives are implemented for example, for synchronization, right? So yes, so we still need this.
Do you know some web resource, cmustdie.com? Some guys from Moscow Institute History start this page to show people about this situation you discussed, and they decide that C language was designed just for PDP-11 machine, and after decides after long times of that, after optimizations, C is not allowed for is not good a choice for hardware programming.
Yeah.
I agree with that or not, that C is not a good choice for hardware programming.
Okay, so to answer to this question, I guess I need to explain my perspective on this problem. So even though I like finished mechanics and mathematics department of university, so like I have a diploma of a software engineer and mathematician, still that I do this work, I feel like I'm doing something like physics in a sense. Why? Because like we like researchers in this area, we don't try to change things around us. We first of all we try to better explain things around us, right? Like physics do. So yeah. So in that sense, I'm interested in like giving like better definition to like better specification for existing C++. I don't believe that in like recent future we'll get rid of C++ or like this approach to shared memory concurrency. So yeah, it's still there.
I think we had a lot of problems with concurrency nowadays, and at least Toyota has crashed cars that was caused by concurrency in algorithms.
Yeah. That is why, as I said in the very beginning, I'm like very keen on like proof engineering and like verifying programs, and yeah, I believe that our future is somewhere there. Then we'll like at least partially verify like very important software. Like for example, Airbus already does. Thanks.